as I promised last time, spaceship is still here. I'm still in space. So we have that. I guess I probably could have been using that when I was just jibber jabbering before. We got the slides. You can see creative destruction is what's on deck, and then we got the whiteboard there. We're integrating nothing. Okay, so yeah, so it's pretty much the same as before. So the other good thing about being online is that like I don't have to do that thing. It's like what did we do last time? I can't really remember what we did last class. So because I can just go back to the video. The video is going to be on YouTube from last class soon. It's still like YouTube has this processing, like takes like a data process or something. But it's going to be there, and then you can see that. But the good thing is I can go back to that and see what we did. So turns out we're going to start on creative destruction. Okay, so let's see. So then I'm going to figure out where to put everything on my screen. So yeah, so we basically finished up the bulk of expanding varieties. Okay, kind of figured out what the equilibrium outcome is, what the growth rate, the share of labor devoted to R&D and production and all those good things. All right, and then we did that in the equilibrium setting or the decentralized setting, which I'll call it sometimes, and in the social planar, and we saw that there was this underinvestment relative to the social planar in the equilibrium setting. Okay, so now we're gonna move on to a slightly different type of model. Okay, and this model is gonna have sort of, it's gonna look, I mean, it's gonna look pretty similar to what we did before. Okay, we're just gonna change kind of one or two assumptions here and there. Okay, and then it'll have sort of different equilibrium properties too, and it's actually a little bit kind of more interesting in a way. It's more, it gets you more thinking about like maybe kind of a real type of firm, not 100%, but like a real type of firm and stuff that we think about in like a competitive setting, or people might talk about in business schools and stuff like that. So yeah, so that's kind of what's on deck. That's called the creative destruction model. Okay, it's we'll see why it's called that, but essentially it's, you know, innovation is still happening in kind of the same way, in the sense that you are well, I mean, innovation happening is actually happening in a different way. It's through the improvement of existing products rather than through the creation of new products. That's the main difference. Okay, but the reason it's called creative destruction is that you're improving the products, but in the process you're also kind of like knocking out your competitors for a time, and so you're destroying your competitor and that old technology that they use, but you're creating something new. Okay, so it's a little bit more. Jacob, what do you got? Yes, I can. Mm-hmm. Yep, we haven't. So yeah, lab equipment is featured prominently, I think, in the textbook in Echamoglu, and I put it up front in previous classes, but I don't know. I think the good thing about lab equipment is that it has like a really simple solution, but it's a little bit weird in how it's constructed. As we'll get there eventually. I mean, I'll give it a less of a treatment because it'll be, you know, we'll kind of know it essentially by the time we get to it. It's sort of like you combine all of your different intermediates, and then at the end you kind of combine that aggregated intermediate with labor, and then you produce output. So it produces like a very linear solution, and that's good, but it's the way that the production function happens never really made sense to me. Mhm. It's both. I mean, it's there's certainly like the general method of going through and saying, okay, find the inverse demand function from the aggregation function, use that to solve the firm's problem. You get sort of a pricing rule of some sort that gives you profits, that gives you value, plug value into the free entry condition, and then you sort of work backwards and get a research share and a growth rate. That whole process is basically unchanged in all of those steps that we do. The things that are different is basically the sort of how innovation happens, the innovation production function, and then the aggregation function is going to be different as well. Okay. Yep. Um, so this should. Yep. Mhm. Yep. Yep. Yeah, exactly. So that's 100% that. The one minor change, which isn't really material, is that because we have a fixed number of product lines, instead of saying there's n, we're just going to say that there's a unit mass. So the integrals are going to be from 0 to 1 now. But I mean, you could change it. It's not an important thing. You could do it with n, or you could do it with 1. But yeah. So like here, so this is going to be our aggregator. It's like a log kind of Cobb-Douglas style aggregation. Okay. All right. So okay, so then let's start down that road. So here, I mean, this you can see, you can review this in the notes, but I'll kind of go through things on the whiteboard for now. Okay, so right, so let's do that. Okay, so this is almost applicable, but I guess I should erase this. Okay, so we're gonna do this is Schumpeter, not to be confused with Schumpeter. Yeah, so basically let's go through sort of the main assumptions and constructs that we're going to be dealing with here. Okay, so y, so I mean we can, yeah, so the y is going to be sort of the exponential of this whole integral log yi di. Okay, so I'm why did I use yi? So I switched from y to c. That's not really super important. I guess maybe I should have done. The notes are saying y. I mean, maybe it is good just so we can keep them separate in our minds. But the notes are, you can think about these yi's as the same as the ci's we had before. Just decided to switch it up. Okay, so right. So this is the reason I call this the log aggregator is that, you know, you can think of it as like the log of y is the integral of the log of all these different yi's. Okay, so that's let's see, that's what Cobb-Douglas looks like, right? So if you remember, like a Cobb-Douglas production function in terms of like capital and labor would look like, if you take logs, it looks like the alpha weighted sum. Okay, so this is like a sidebar. This is not applicable to what we're doing, but if you had a Cobb-Douglas production function that looked like, you know, k to the alpha, L to the 1 minus alpha, then that means it's the alpha weighted sum of those inputs. The logs are the alpha weighted sums. Okay, so same thing here. It's just in an integral form instead of a sum form, and we have a continuum of products. Okay, so this is like, yeah, sidebar. Okay, so then all right, and so why do we do that? There are good reasons to. So one question you might have is, why do we switch to log aggregation? Why do we switch away from that epsilon, that general CES? Especially because we know that this is a special case of CES when you take that epsilon converging to 1. Okay, so essentially it's just to make things easier. Okay, what we're gonna see, and actually, so Yicheng went over this, I believe, in recitation, at least in part, thinking about different types of pricing rules. Okay, so when we did expanding varieties, the assumption was that you're new, either if you're an incumbent or a new entrant or whatever, once you show up in the market, you're a monopolist and there's no competition that you're facing. Okay, so you just choose whatever is best for you. Okay, so that's going to be a little bit different now because we're not creating new products, we're improving existing products. And because we're improving existing products, there's always going to be that firm that came before you. Okay, so we're assuming sort of infinite past. There's always going to be some firm that came before you, and they're going to provide your competition. Now, they're going to be imperfect competition. okay, they're not going to have a productivity as good as yours because you're the state of the art. You've improved on their productivity. The assumption, that's the assumption. And so they'll provide sort of partial computation. So it's going to look like a Bertrand setting with different marginal costs. Okay, that's going to be the outcome. And because of that, the pricing problem is actually in general fairly complicated. Here we'll see that it's not going to be that complicated. It's going to have a simple solution, and part of the reason for that is because of this aggregator that we assume. Okay, so we'll see exactly how that works out in a moment. Okay, so let's do this. Okay, all right. So the next steps here are going to be find that inverse demand / demand function from the optimization of the firm, and then the aggregating firm. Okay, and then plug that in for the monopolist. Or actually, they're not monopolists anymore, for the intermediate producer. Okay, yeah. So let's do that. Okay, so at this point, okay, what we know is that you've got should I do this? Okay, so you've got usually the way we write these aggregators is with sort of like a wedge. Okay, so it's like kind of like in game theory, these sub games, except backwards. Okay, so we have these different yi's. Okay, and actually the yi's are produced with labor. Okay, and then that labor has a certain productivity. So this qi is the technology of that producer. Okay, so those get combined into eventually some final good y. Okay, so this is small, but this is a little yi here. Okay, and so there's a bunch of these. Okay, so there's 0 to 1 here for those i's. Okay, and then each individual producer has some productivity. Okay, then that gets combined into the yi. And the way that the final good aggregation market works is the same as before. You've got some sort of competitive process for this aggregating firms that are operating this technology here, and they take in those yi's, they buy those yi's given a posted price. Okay, so but it is important, this before we would just have yi equals li, and this thing was expanding, that this upper bound n was expanding. Now the upper bound is there's a constant number of products. These QIs are what's getting better. We're getting better at making these products. Okay, and over time, you start at like some Q0, you improve it successively by some factor lambda. Okay, so this is like Q0, Q1, which is 1 plus lambda times Q0. Then the next firm comes along and improves it again, so 1 plus lambda squared. So it's proportional improvements up what's called this quality ladder, and you keep going forever. Okay, so that's the way that innovation happens, is this: you increment the productivity. When you're successful, you come up with a new way of producing something. You increment the productivity by a proportional factor lambda. So the new productivity becomes 1 plus lambda times the old productivity. Okay, that's the basic setup. That's why it's called a quality ladder model sometimes. Okay, so all right, so that's, keep that kind of on the back burner for now. Okay, we'll talk about how Q is important and everything like that. Okay, but for now we just want to find what's the inverse demand function here. Okay, so and that's, so we're going to say, okay, it's the same as before. Okay, we're going to say, well, max the revenue of that aggregation firm. Okay, the price of this output is assumed to be 1. We're normalizing that, minus all of their costs. So they're buying a bunch of yi's at price pi. Okay, so the intermediate firms have already posted their prices. Let's say they're choosing how much to buy. Okay, so, and that's max over like all the yi's, like whatever the notation for that is. Okay, right, and so then there you kind of get something relatively simple. Okay, again, it's sort of like the derivative for each individual I, or for almost all I, should be 0. Okay, So what do we get? So you take the derivative here. You're going to get this whole thing back first because it's an exponential. And then that's just y. Okay, so let's save ourselves a bunch of virtual ink here and just write y. And then the derivative of what's inside for a particular I is going to be 1 over yi. So we're going to get y over yi. All right. And then minus what? Well, we're just going to pick up a pi. Okay, so this is like the del yi. Okay, so that's pretty simple. Okay, not too bad. And then so here, if you want to, so if you want to think about it as an inverse demand function, well, then it's just p equals y over yi. Okay, the more you want to sell, the lower the price you're going to be able to fetch. If you want to think about it as a demand function, well, I think we can handle that. That's going to be yi is y over pi. The higher the price you post, the less you're going to sell. Okay, very simple game here with the sort of epsilon equals 1 Cobb-Douglas case. Okay, so all right, so that's good. Okay, we don't even have to worry about all these epsilon exponents jumping around anymore. We just have 1 over whatever. Okay, so that's another beauty of the Cobb-Douglas form. Okay. All right, so the other thing I want to note, which is this is much a property of this production function, is that you can also see that if you just look at pi times yi, which is, well, this is going to be the cost that these firms are paying. It's also going to be the revenue of the intermediate firm. Okay, this is going to be equal to y. So we already kind of talked about this a bit, but we can see explicitly this is going to be equal to a constant. So this is the same reason that things blow up when we go to epsilon equals 1 in the expanding varieties case, is that if your revenue is constant, you're just going to try and minimize costs. The way you minimize costs is by producing almost nothing, and the way you produce almost nothing is by setting an insanely high price. Okay, this is why things blew up when we looked at this in epsilon equals 1 case in the expanding varieties. Okay, but it's still true, and we're gonna, because you're now going to have a competitor kind of trailing you, it doesn't let you do this, set the price to infinity thing. Because if you set the price to infinity, I'm going to buy from your competitor. Okay, so it puts some restraint on the sort of level of monopoly that can occur, and it allows us to step into this otherwise forbidden epsilon equals 1 zone. Okay, so, and it makes things simpler. Okay, so that's, things kind of just work out in that way. Okay, so this is kind of what we needed. All right, this, either of these two, because they're kind of equivalent in most cases. This is like a demand setup for good I, given like a price and everything. Okay, so and with that, then we can step into the problem of the intermediate producer. Okay, so let's do that. All right, so now we're thinking about intermediate producer. Okay. All right, so remember, let's just lay out what, Jacob, you had a question, a comment. Yep. Yep, little y. Yep. Okay, so yeah, so their production technology is yi equals qi times li. So qi is, so here also we want to be sure that we differentiate between products and intermediate firms, the producers of that product, because who is producing, there's churn, there's turnover in who's producing the product. Every time you improve it, you kick out the old person, as we'll see, and a new one comes in. So the identity of the firm producing that product is going to be changing over time. However, that's actually not that important, because there's only going to be one firm at a given time producing that product. Okay, and so it's really not that important who it is. The only thing that is important is what's the productivity at which they're producing that product, qi. Okay, so qi, the state of the art qi for a given product is what characterizes the state of that product line. Okay, that variety. Okay, so so qi is going to be important here. Who exactly what the name of that firm is, we don't care. So but we just care how good they are, right? So that's that's going to be important for each individual product, and sort of the state of technology right now is going to be the vector, the infinite dimensional vector of QIs. From 0 to 1, we'll see that there's an aggregation that's like a sufficient statistic later on. Okay. Okay, but for now we just need to think about this linear technology. Okay, and then the profits. Well, that's just sort of kind of always true in some sense, which is the revenues pi times yi minus w. Same setup as before. They use some labor at wage w. Okay. Okay, so all right, so we've seen already, you know, if they're just left totally unchecked as a monopolist, they're going to go crazy, mad with power, and charge a insanely high price. Okay, so we're gonna not have that. What we are gonna have is their competitor reining them in. Okay, so the competitor is not actually going to produce. It's just the threat of the competitor being able to produce is going to limit what they can charge. Okay, right, and so essentially you can think about it like this. So this is what's called limit pricing. Okay, and this is, I believe, what Yu-Chun was talking about in recitation. Okay, so what we're gonna do as the leading firm, okay, they're not a monopolist anymore, technically speaking. It's weird because, you know, if you looked at it in the data, there'd only be one producer. It'd look like a monopolist, but they're not exactly a monopolist in the way that we think about it here. Okay, because they have a theoretical competition. So there's limit pricing. What they're going to do, this leading firm, is just they're going to set, they want to set the price at infinity. If they were left unchecked, they would set the price at infinity. They're going to set the price as high as they can, such that the trailing firm does not enter. They're just going to keep that trailing firm out. Okay, and if you think about that, okay, so they're going to go as far in the direction of their optimum as they can, with the constraint that they want to keep the other trailing firm out. Okay. Now, if you think about the profit of the trailing firm, if they were to start producing, it would be, you know, their price minus their cost times whatever quantity they produced. Okay, so their price margin, P minus W, times whatever quantity they produced. Okay, and if you get to a point where the price, okay, so actually here I should be more specific. So this is going to be true for whatever firm is. This is pi yi minus w times li. So li is yi over q I. Okay, so we're just plugging in there. So now this is purely in terms of y, and we can combine this pi minus w over qi times yi. Okay, so this is a way to state the profit level of this firm, which is price minus the marginal cost is w over qi. You got to pay the wage. QI is your productivity. Higher productivity means lower marginal cost. Okay, so this is, remember this is their marginal cost for and this should be MC MC sub I. Okay, so that's their marginal cost. So this is for any firm. And now if you think about it as the trailing firm, okay, sometimes I'll write the trailing firm as like minus I, like in game theory. Okay, so if you think about the trailing firm, their profits is, you know, it's going to be the price margin, P minus W over QI times the quantity. If it were the case that the price that they were facing, like when they were thinking about just producing that first initial unit of goods, the price they were facing was already equal to their marginal cost, they wouldn't want to produce, okay, because they'd be making zero profit on that. And if they produced a little bit more, they'd push the price down even more. Okay, you can see here, if they produce a little bit more, they're going to push that price down, so they're going to make it even worse. So they're never, if they're like at zero and the price is already equal to their marginal cost, they would not want to produce. Okay, so that's limit pricing. Okay, the limit pricing would say that the leading firm, P sub I, is going to set their price equal to the marginal cost of that trailing firm. Okay, now if you're the trailing firm, you see, okay, the prevailing price is PI, it's equal to my marginal cost. I'm not making any profits I'm at least weakly happy to not produce, and that's that's good enough. Okay, that constitutes an equilibrium. Okay, and you can see that it's not, the weakness isn't a problem in the sense that if they were to produce any amount more, they'd push the price down more and they'd actually start making negative profits. Okay, so really they cannot make positive profits whatever they do. Okay, so that's the essence behind limit pricing, is you just need to think about, you're the leading firm, you want to keep that trailing firm out. Okay, all right, so then let's figure out what does that mean exactly. So that's marginal cost here is W over Q minus I. Okay, now what is Q minus I? That's the firm right behind you. Okay, so the firm right behind you, they're going to have your productivity, but a little bit worse, and the factor is going to be that 1 plus lambda. Okay, so remember, so I didn't say this 100% explicitly. Lambda is the innovation step size. Okay, so this is important. It's when you do a successful innovation, how much do you improve the productivity by? So let's say it's 10% or something. So every time you come up with an idea, you figure out how to make this product with 10% higher productivity, which means with 10% less labor as an input. Okay, so it's a labor saving. That's the assumption, is labor saving in some sense. Okay, so that's going to be important for like the growth rate and stuff like that. Okay. Okay, so then here, so Q minus I, that firm right behind you is just kind of your productivity divided by that factor, right? Another way of saying is your productivity is the old productivity Q minus I times 1 plus lambda. Okay, so yeah, so then if that's true, then this is W. Okay, and then this is QI over 1 plus lambda. Okay, which is 1 plus lambda W over QI. Okay, or like, yeah, which is 1 plus lambda times your leading firm's marginal cost. Okay, so essentially with this limit pricing, we now know what price this leading firm is going to choose, and we know that they're going to be the only producer because they've convinced through certain means, they've convinced the trailing firm not to enter by setting the price low enough. Okay, you can also see that their price is going to be higher than marginal cost. They're going to be making money, and they're going to be making money in proportion to lambda, how big lambda is. Okay, so things kind of work out, right? Okay, and so here, so the idea is they're going to set this price. If you want to think about it in terms of quantities, okay, they're going to produce enough YI so that the price is low enough that trailing firm doesn't want to enter. Okay, so they kind of keep their volume high enough so they keep the price low enough to keep the trailing firm out. That's the idea. Okay, so once we know their price, then we're almost all set. Okay, so so full summary here, PI is equal to 1 plus lambda times the lambda times W over QI. Okay, so that's number one. From the demand function from the aggregating firm, which says that Y is equal to Y, little yi is equal to capital Y over PI. Then we're going to get this. Okay, so now it's like, so 1 over P is like 1 over 1 plus lambda QI over W times Y. Okay, so that's their production. Okay, that's how much they're producing. Okay, but either way though, regardless of anything that we found with regards to pricing, it's always going to be true that PI times Y is equal to Y. The revenues are actually still always capital Y. Okay. All right. So we kind of know everything. We know the price. We know the quantity. We know the labor if we want to. Right. So labor is just YI over QI. Okay. If they're producing YI, we can back out what their labor is. So that's just going to be this thing minus the QI term. Okay, so like 1 over 1 plus lambda times Y over W. Okay. So so right now we got, you know, the wage, of course, is still undetermined. We'll figure that out in a bit. Okay. Um, we can figure out, well, actually we can figure it out pretty darn soon. You can see already like the way that things are kind of going to balance out is W is going to be growing at the same rate as output. Okay, so this ratio is going to be you know, constant in steady state. Okay, and then that means that, you know, you're going to get some non-growing amount for Li. Those are going to integrate to the total production labor, and so everything's going to kind of be nice and work out. Okay. Yeah, and so and if you want, so you know, because W is going to be growing at the same rate as Y, we can define W tilde. That's it's not up to my standards for W's. Okay, so we're going to have W tilde. Let's see. There we go. Which is which is W over Y. So W tilde. W over Y. Pretty standard. Normalizing things by Y. We're going to throw on a tilde. Okay. All right. So okay, so that's kind of what we're gonna get. You can do that here too if you want. This is gonna you could turn this into a 1 over W tilde as well. Okay, we don't have to, but you can. All right, so so we kind of know everything about what these intermediate firms are doing. Okay, and at this point, there's kind of two things that we're gonna want to do. Okay, one relates to the product market, one relates more to the research side. Okay, so on the product market side, well, we have these W's and Y's floating around. We may want to figure out what exactly are those. Okay, that's one thing. And then and that's going to come from sort of aggregating things up and making sure that everything's consistent. And then we also have we're going to want to find profit at some point and figure out what the value is and plug that into the free entry condition. Okay, so let's do this one step at a time. Let's figure out entirely what's happening on the production side and then move into the research sector. Okay. Okay, so now it's the same as before. We have, yep, sure. Mm-hmm. PI. Let me think. So let me check the lecture notes here. So that might be, let me think. You know, yeah. Yeah, okay, so yeah, sorry. That's a typo. If you look at the YI right below that, that's correct. Yeah, so the PI should be 1 plus lambda. Okay, so let me, yeah, I don't have a physical pencil anymore. Let me write a note. Fix PI. Notes. Okay. Okay, thank you. All right, so then, okay, so, all right, Jacob, you're good now? Or you got another question? Okay. Okay. Yeah, just wanted to double check. Okay, so all right, so now let's do the production side, and then we'll move on to the research side. So for the production side, it's labor market clearing is going to be an important thing, and then sort of basically aggregating Li to get a labor market clearing condition. It's going to give us one of W and Y, okay, or like a part of it, and then aggregating Y here is with the aggregation function is going to give us like that other part. Okay, together with those, we'll get both W and Y. Okay, so let's do labor first, I guess. Li. Let's keep it in unnormalized terms for now. Okay, so Li is going to be 1 over 1 plus lambda, just kind of repeating, times Y over W. Okay, and then if we integrate that, so P, we're going to call total production labor, which is the integral of all these little product lines, how much labor they're using. This is an integral sign. Okay, and what's that going to be? Well, so that's pretty simple in this case. It's a constant integral. Okay, we don't have anything really to do, and it's a unit integral, so there's no issue of picking up factors of n. Okay, so it's just that. All right, it's a very simple game. P is equal to 1 over 1 plus lambda times y over w. Now, yeah, I mean, so what this is saying is that, conditional on a certain y, the higher that the wage is, the less production labor you're going to use. Okay, so this is like a supply of labor kind of thing. Okay, or the demand for labor kind of thing. Okay, and then we're going to use that later. Okay, so the other way you can think about this is a labor share statement. If you rearrange it, you're going to get WP over Y is equal to 1 over 1 plus lambda. Okay, so this is a production labor share statement, just like before. Now instead of being a function of epsilon, it's going to be a function of lambda. Okay, essentially the idea is that we'll see in a bit that lambda is going to determine profits. Okay, lambda is going to determine profits because if lambda is very small, that leading firm is not going to be making many profits because they're practically identical to their trailing firm, Bertrand, 0 profits. Okay. And if they're making 0 profits, then the profit share is very small, which means the labor share must be large, which means that this would be close to 1. Okay. Conversely, if lambda is very large, they're almost like a monopolist. Their trailing firm competition is extremely, not productive. And if they're almost like a monopolist, they're going to be making a lot of profits. And you can see here that means the labor share would be small. Okay, so we'll see the flip side of that on the profits later on. Okay, but for now, essentially, the important thing is P is equal to 1 over 1 plus lambda times y. This is just definitional. Yep. That's what we're calling P. This is going to be, this is still in that, like, 1 equals P plus R. So this is still related back to the research share as well. Okay. All right. So now, so we have that. That's sort of like number 1. That's going to be useful. The other thing we're going to want to do is think about, let's go back a little bit, is think about, oh wait. Okay. We have a oh, I didn't see these chats. Okay, let's see. Dor, sorry, I missed your chat from before. I wasn't keeping a close eye on the far right side of the window. We can, let me know if you want to talk about limit pricing. Or no, I did repeat the limit pricing. Okay, so it seems like we worked out on that one. Okay, we got the y is p equal to the integral, so p is just the number of workers. Yep. Yeah, p is the number of production workers. Okay, so there's the same as in expanding varieties. There's a unit amount of total workers. Okay, p is now p and r are like equilibrium variables. They're representing what's the aggregate allocation, and they're solved for in equilibrium. And then so p is the total production labor, which is kind of like, that's all we really need to find the wage in some sense. Okay, so like the other way to think about this is that the wage is equal to 1 over 1 plus y lambda times y over p. Okay, the more production labor is, the lower the wage. Okay, so yeah, so but p is an equilibrium variable, and then r we'll see is determined by the free entry condition. Okay. All right, so then let's look at yi here. So we did the labor aggregation. Now we're going to do the goods aggregation. Okay, so we're going to have this yi. Let's see, what's the best one to use is 1 over 1 plus lambda times let's say times qi. Okay, and then times y over w. Okay, so if we want, we could plug in what we know so far. Okay, we know y over w. Okay, yet another construction of this is to say that y over w is equal to 1 plus lambda times p. Okay, so Yeah. So then we can plug that in here. Okay, so we kind of know y over w from the labor market clearing condition. We can plug that in here. Why not? So 1 over 1 plus lambda times qi times 1 plus lambda times p. And what do you know? We have a canceling event. Those 1 plus lambdas will cancel, and we just get qi times p. Okay. So what does this mean? Well, here's essentially what this means is we know. Yeah. Okay. Actually, you know what this means? This just means that if you, it actually comes from the labor allocation. If you do the same thing for labor, okay, if you do the same thing for labor, plug in what we know now that we've solved for labor market clearing, that the wage basically y over w is equal to 1 plus lambda times p. If you plug that in here, you're gonna get 1 over 1 plus lambda times 1 plus lambda times p. You're just gonna get p. Okay, so essentially what we find is like, okay, we maybe we should have seen, not we, but like, you know, it's something you can sort of, in retrospect, it makes sense, which is the labor allocation is constant across product lines. It is not a function of Q, okay? Which is actually a little bit weird, okay? And it comes from the Cobb-Douglas assumption. You have all these product lines with different productivities, QIs, and at the end of the day, you decide to put the same amount of labor into each one. You don't say, oh, let's put more labor into the more productive ones. Nope. Because of the Cobb-Douglas, it exactly evens out that you put the same amount, okay? Because there's always two ways you can think about how productivity affects this allocation. One is QI is higher for a particular product line. Let's put more labor in there. That's a good product line. Let's put more labor in that and allocate more labor and make our overall output higher. That's one way to think about it. The other way to think about it is, well, QI is higher, it's more productive. So if we want to produce however much we need, we can actually put in less labor and get the same amount. Okay, so you can always spin it both ways, and they kind of both make sense. And what decides that is what demand looks like. Okay, if it's something where you just kind of need a certain amount, which is to say demand is inelastic. Jacob, you got a question? What's up? Yep. Mm-hmm. The second one. So for each product line, there is a single firm that produces that. Yeah, yeah. So the outcome is a monopolistic outcome, but we can say that they have competition that keeps them honest in some sense, but they don't enter. Yeah. No. So all we know right now, which is kind of enough for our purposes, is that when they do improve it, they improve by a factor of 1 plus lambda, basically. Yeah. Yep. Just that one. Yeah. Mm-hmm. Okay. So yeah, the question is, how do we allocate this labor, and you can kind of give intuition for going either way, and the elasticity of demand is what decides that. If it's inelastic demand, then you go with the second one. You say, well, we want to produce this amount. we can use less labor to do so. So let's use that labor elsewhere where it's needed. If the demand is highly elastic, people are like, if you can produce more of this, I'm all about buying it. Then you say, okay, well, now we're gonna induce this positive correlation between L and Q. The higher Q product lines, we're gonna put more labor into those because people will still be buying that. Okay, so it's not just the sort of supply side technology, is also the demand that determines that. Here, Cobb-Douglas is sort of a midpoint in production functions, in aggregation functions, such that you get exactly that those two intuitions kind of cancel out, or you're right on the edge of the deciding line. Okay, so you get when you first get, you say, okay, well, we know that the labor allocation is constant across product lines, not a function of QI or I, and it's equal to something. Okay, but then if you think, okay, well, if it's constant and there's a unit mass of product lines, then in fact, and we know the total, then each individual one has to be equal to that total. Okay, so that when you integrate it, it adds up. Okay, so at the end of the day, you get Li equals P because of the unit mass that integrates up in the proper way. Okay, now, and then if you want to map that to Yi, well, immediately, if you know Li is equal to P, then Yi from that production function is Q times L is just Qi times P. Okay, so we get that too, that Yi, so sort of the summary here is that Yi is equal to Qi times P. Okay, cool. Okay, so now all we have to do is run this through the production function, and we're going to be all set. Okay, so the aggregation function. Okay, so that says the y is equal to this exponential log integral thing. Okay. Okay, so what do we get? So this is constant returns to scale, right? So remember, if you have log and the integral is from 0 to 1, it's constant returns to scale. Okay, we know that so we may as well spread it out. So this is 0 to 1 log of p qi. I don't know why I reversed the order. Okay, that's just all right. P qi di. Okay, so we know plugging in that's going to be true. We also know that the p is it's going to factor out. Okay, so but if you want to go through the steps, it's like you split this up into a sum. So the log p plus the log of q. Pull out the integral, you just get log of p. Pull it out even farther, it's going to become regular p again. So this is going to be p times e to the integral from 0 to 1 of log qi di. All right. Okay, so now what is that? I mean, so now we know it's output is equal to production labor times some function of q, all these qi's. Okay. So it turns out that that's good enough. This thing here is our Q aggregation. We're going to define that like this. Okay, so which is to say, if Q is equal to so Q, like definitionally, I'm defining it is equal to this aggregation. Okay, so it's just the log aggregation except with Q's instead of Y's. Okay, so this is like a index of aggregate quality here. Okay, it summarizes all the information about the productivities of the different QIs into the only thing that we really need to know, which is capital Q. All right, so okay, and if you define that, then Y is equal to P times Q, the production times the productivity on average. Okay, so this is it. Okay, so yeah. So yeah, that sufficient statistics that I alluded to before is Q. Okay, and that's the way that we can combine all these things. Okay, so now what can we do with this? All right, so this is useful. Okay, it's going to be useful later on too. The fact that we define Q and then we can express output just as a function of production labor and Q, because like when we want to later on when we want to know the growth rate, okay, it's essentially going to be the question of what's happening to like P is going to be like constant, and the question is Q growing? It's going to be growing, and it's going to be growing because each of these QIs is, over time is getting bumped up by new innovations, by those 1 plus lambda factors. Okay, so and we're going to be able to express exactly, given the sort of rate of innovation, given the size 1 plus lambda, what's the overall growth of Q going to look like? Okay, so that's going to be something we can compute, and that's going to give us the growth rate of output. Okay, so that's the basic idea, is that we can compute the growth rate of Q with other aggregates, and then hence get the growth rate of Y. Okay, yeah. Okay, so that's basically the production side. We know Li, we know Yi here, we know capital Y, we know the wage, like we know all sorts of stuff. Okay, so usually the way we do it is you solve for the whole production side conditional on like P, on the aggregate labor allocation to production. That's sort of like the best you can do. Conditional on P and conditional on some statistic of technology. In this case, it's Q. In the expanding varieties case, it's N. Okay, some aggregate statistic on technology. Okay, so and keep in mind that it's for every model that you could ever possibly write down. It may not be the case that you can have sufficient statistic. It might be that the whole distribution is important in some way. It's just that we wrote down this model so that we could get a sufficient statistic. That makes our lives a lot easier. Okay, so all right, so that's it. That's production side, and now we can move on to the research side. Okay, so that's all production. Okay, so let's think about research. Okay, any questions? No questions. Good. So with research, we're gonna do find profits from the production side, find value, plug it into the free entry, and then do a bunch of algebra. Okay, so cool. What do we get? Profits. Okay, I guess this is still sort of technically part of the production side, but whatever. It'll look like that. Okay, we can just plug in everything we know. Okay, so we know that this is yi. Okay, and if you want to, pi is just going to be capital Y over that. Okay, at the end of the day, we know that pi times yi is always y from the demand function. Okay, so we could plug in individually. We could see it cancel, and we're going to get y. And then here, w times li. Okay, so what is w? Okay, so we can plug in for w because we know that, which is right here. Okay, so we're still keeping this y around. Okay, we could plug that in later, but we're going to keep the y around for now. We know w is 1 over 1 plus lambda times y over p. Okay, and we know that L is just equal to P from up here. Okay, it's going to cancel. Okay, so what do we get? We get y minus 1 over 1 plus lambda times y again, right? Which is, what's that going to be? Well, it's going to be, you can factor out the y, then you just get 1 minus 1 over 1 plus lambda. It turns out that that's lambda over 1 plus lambda. Okay. It's kind of confusing because y and lambda are vertical mirrors of another, but that's lambda, that's y. Why does pi yi equal y? So that's not even something, we don't even need to solve the production side for that. That comes from this demand function, right? So when we derive this demand function, it's what's called unit elasticity because the exponent here and here is equal to 1. Okay, another implication of that is that the total revenue or cost you're pulling in is y. Okay, it's just a Cobb-Douglas thing. It's the same as, it's like the cost shares are constant in Cobb-Douglas. It's the same manifestation of that. Okay, so okay, so to then summarize, pi I is equal to lambda over 1 plus lambda times y. Okay, if you want, you can oftentimes, that's an arrow, oftentimes we'll define normalized tilde pi I, which is defined to be pi I over y. Okay, so that would just be 1 over 1 plus lambda. Okay, and in fact, this is that other side of the income allocation. So remember, we found here. Okay, where is this one? Yeah, so here we found the labor share, the production labor share, 1 over 1 plus lambda. Sorry, this should be lambda. So dividing, I just forgot the lambda term, lambda 1 plus lambda. That was the labor share. The profit share is 1 minus that lambda over 1 plus lambda. Okay, so then we can see, pi I plus WP is equal to y. Okay, that's a GDP kind of, yeah. And now this is really like the integral of pi I because they're all the same. All these the profits are the same. That's the other thing I didn't mention. Profits are the same for every individual product line. Okay, because they all have the same lambda. They have different quality. They have different productivities. QI. They all have the same lambda though, and that's really what determines profits. Okay, so that's an important result. Okay, so yeah, I mean, if they had different lambdas, if let's say lambda was random instead of deterministic, then they'd have different profits. But in this one, they have constant profits. Okay, so that makes our lives a lot easier, in fact, because Jacob, you got a question? Mm-hmm. Yep. And it's because they're all, every firm is facing the same kind of competitive fringe of that next one. So think about it like this. Um, in a more general setting, let's say we had different firms were better or worse at improving productivity. They were better or worse at innovation and research. Then maybe the better firms would have larger lambdas when they do succeed, and they would have higher profits. Okay, so it's just it's a particular result from these assumptions. If you wanted to like really generate some notion of better seeming higher tech firms having higher profits, you would have to introduce another thing such as they have higher lambda. Another thing you could do is which gets into kind of exactly how the research production function is defined here. Everything here is like externally facing. All you're ever trying to do is capture a product line from another firm. So you do some research, it kind of lands on a random victim or target product line. You improve that, kick the old firm out, and start producing. Okay, so it's very much like all external competition. Technically, in this one, you only have one. There's a very interesting and popular extension of this type of model called the Cutting-Kortum model, where you can have multiple product lines, and it gives you a really neat predictions for firm size and the firm size distribution. So that, yeah, yeah. Sorry, I partially misspoke earlier. It's not. It's really it's all entrance. Okay, so it's all externally facing. Everyone is just it's just entrance coming in and taking out the incumbents. That's the cycle. Yeah. Yeah, exactly. So yeah, but I because in my mind I think I was partially thinking of this Cutting-Kortum model, which is sort of the next step down this road. So we'll do that Cutting-Kortum model by the end of the term, and you'll get kind of more interesting stuff going on there. Yeah, the other thing is relating to that how it's set up is like just to give you more perspective about like where does this lie in the space of possible models, which I think is important to think about. You know, like why did we choose this one? You know, what's going on here, as I just mentioned, is all entrants still, and they're taking out existing incumbents. Okay, so the thing, and that's important. Okay, and that's the most creatively destructive. You know, if you want to call it what they call it nowadays, would probably be like disruption. Uh, that's the most extreme manifestation of that because it's like some complete outsider comes in and takes out the incumbent. Okay, that's the so this is a very extreme example in some sense. Uh, the other types of like source target innovation you could think about are, as you know, like in the Cutting-Kortum model that we'll see, existing incumbent firms trying to take products from other incumbent firms. Okay, so it's like a Google trying to steal market share from Apple or something like that, or even from Google trying to steal market share from like another industry by utilizing their technology. Um, so that'd be more like within incumbent, but still sort of externally oriented with regards to the firm. And then the other one would be completely internal. So you're your own firm. You have the product line. You're just trying to get better at making it, and that's obviously something that firms do. Okay, so and that last one, internal innovation, is really the big thing I think that's missing here. And if you had internal innovation, that it's essentially internal innovation would allow you to change your lambda over time. So when you would do internal innovation, you get farther away from your competitor, and you actually get more profit. So firms would have an incentive to do that even in this model. Okay, so it is definitely something that's missing, and it's a big part of innovation. And so that's something to keep in mind. Okay, the only thing to also note there is in terms of the efficiency properties. We'll see efficiency properties are very different for internal and external innovation. Okay, because with internal innovation, you literally internalize all of those gains. Okay, but you internalize some of the gains, but you don't necessarily internalize all of them. Okay, And so that's one thing. Whereas with external, you know, it's good stuff because you're acquiring wholly new market share. Okay. Whereas with internal, there's a sense in which you might be sort of cannibalizing your own existing sales. Okay. So that's something like cannibalization, something that people talk about in strategy, kind of business school style strategy stuff. Okay. So, all right. So, yeah, so that's sort of the lay of the land more generally. Okay. Now here, given what we have, basically we know profits now. Okay, so now we can map that into a value function. Okay, so now the value function is a little bit more interesting here. Okay, so remember, what did our value function of old looked something like this? Okay, so this is value. Value function of old looks something like this. We'd have like this sort of, you know, RV minus V dot form that you always get on the left side is equal to some flow profit value. Okay, and that's kind of what we had. That's all we had at the end. Okay, there's one wrinkle here, which is that you don't last forever anymore as a firm. You get kicked out at some point. Just, you know, sort of like you were born by the sword and you will die by the sword. You were born through creative destruction, innovation. You kicked another firm out and started producing, but there's going to be someone coming after you later. So, the firm time horizon is a little bit shorter. It's potentially artificially short in this setting. Okay. So I'll tell you what the answer is, and I'll show you how we get there. But the answer is going to be basically, if you've got some rate of what I'll call a creative destruction, which is the rate at which you get kicked out, okay, then you're going to get an extra term, which is going to look like tau, that rate, times your original value function. Okay, so I'll show you how to derive this in a second. But if you rearrange things, okay, then that's going to look like r plus tau vi. That's vi dot, okay, and then equals pi I. So what the tau does is it basically modifies your effective discount rate, which makes sense. Okay, it's just like the death rate. If you put in a death rate for a consumer utility, you get that it ends up modifying the discount rate. Here it modifies your effective discount rate. Okay, so why is that? So we have. I'm gonna go a few minutes. I'm gonna go like 5 minutes over because I started exactly at 10:30, and then I was chit-chatting a little bit. So I'm going to go like 5 minutes over. Okay. So basically, if you think about deriving this from a discretized form, what's that going to look like? So it's going to be like, let me just write V. Okay. So like I'm going to write V equal, instead of VI because we know they're going to be the same. Okay. So V of T, not plus delta, V of T, okay, is going to be equal to delta times pi I. So the delta here is our little small time step, okay? It's a small number. It's much less than, I don't know how to write it. It's much less than 1 or something like that, okay? It's like an epsilon time step, okay? So you're going to get some, for that first delta, you're going to get some amount of profits, okay? And then we're going to discount the future, and the way we're going to do that is minus delta R. So R is the firm's discount rate, okay? And then what do you get in the future? All right, well, this is where things get interesting, okay? So with some probability, delta times tau, you're going to get knocked out, creative destruction. In that case, you just get 0 forever. You exit as a firm. You become that second firm, the lagging firm, and you decide not to produce, and you never produce again. Okay. So why is it delta times tau? Okay, so tau is a rate of creative destruction. It's what's called a Poisson flow rate, a Poisson process. That means that over a sufficiently small increment of time delta, the probability of this happening 1 or more times is just going to be delta times tau. That's a property of a Poisson process, is that it's independent across time, and for small time steps, delta the probability, as in the 0, 1 probability, is delta times the rate, in this case tau. Okay, so this is going to be tau, delta tau times 0, plus, okay, then the probability that you don't get kicked out, 1 minus delta tau times your value going forward, which is going to be t plus delta, so it's like the continuation value. Okay. Right, so that's pretty much it. Okay, we're going to be able to derive this before the end of class. Okay, so then what do we get? We get plus 1 minus delta r, and then 1 minus delta tau, v of t plus delta, and we don't even need that. Okay. Sorry. That's right. Yeah. All right. Yeah, that's right. Okay. Okay. So then, what can we do with this? All right. So now we need to be a little bit smart here. Okay. Now, so we can kind of expand this a little bit. Okay, and simplify things. Okay. So we're going to get the one term is going to give us v of t plus delta. Okay, then we're going to get like a minus, for the cross terms, we're going to get minus delta r plus tau, v of t plus delta. Okay, now for the what we would call the L in the FOIL term, the last term, we're going to get a delta squared. Okay, turns out delta squared, we don't need to worry about those. Those are infinitesimally, there's like infinitesimal and infinitesimal. Okay, so we don't need to worry about delta squared. So that's why I'm writing like approximately and then dropping it. Okay, so it's really going to look like that. Okay, and then from here, we're going to do the sort of normal, like turning it into a derivative thing. Okay, so if we do this, how should we say this? So subtract that v of t plus delta. Okay, and divide by delta, then that's going to be equal to pi I minus r plus tau v of t plus delta. Okay. All right, and then just take a limit as delta goes to 0. Okay, so here we're going to get, so this is like a inverted, it's a minus v dot. Okay, it's equal to pi. Okay, so I guess I just write pi. We don't need pi I because they're all constant across I. Pi minus r plus tau times v. Okay, and then we can move this over to get r plus tau v minus v dot is equal to pi. Okay, that's our answer. And you can see that's exactly what I have here. Minus the i's, r plus tau v minus v dot equals pi. Okay, so that's how things work when you have potential stochastic events that can happen to you, such as this tau created destruction shock. You can work it in with probabilities. Just you need to know that for Poisson processes, the probabilities are linear in time and rate. Okay, and you get this. Okay, there's another, and so that's like the sort of deriving it from the discrete limit. There's another kind of intuitive way to construct these for more complicated settings that I'll talk about next time, which is very like straightforward. You can throw in different events that can happen and like all sorts of different stuff, and it all works out fine, and you don't need to worry about dealing with deltas every time you want to drive it. Okay, so all right, so that's pretty much it for today. We've basically gotten to the value function, or it's not a value function, it's just the value. We'll plug that into free entry next time and actually solve for the equilibrium.